precession around black holes in two different contexts. The first one concerns an accretion disk that forms after a tidal disruption event by a supermassive black hole, while the second one involves low mass history binaries, so stellar mass black holes. So, a tidal disruption event occurs whenever a star wanders enough close to a supermassive black hole to be torn apart by its tidal field. This means that the pericenter radius of the orbit of the star is of the order of the tidal radius, which is given by the mass ratio, the 1/3 times the radius of the star. So here you have the black hole, and then the star that passes by. So usually one defines the impact parameter of the encounter as the ratio between the tidal radius and the pericenter radius. And if this is greater or at least equal 1, the star is disrupted. So then the stellar debris start coming back to the pericenter after a time which is roughly 41 days for a 10 to the 6 solar masses black hole, a solar type star, and for an impact parameter of 1. They start coming back to the pericenter with the fallback accretion rate, which is given by the peak accretion rate time over the mean to the minus 5/3. So this is taken as a typical signature of the tidal disruption event, and here n dot p is this quantity and is roughly 2 orders of magnitude above the Eddington threshold for 10 to the 6 solar masses black hole. Okay, so typically tidal disruption events have a very bright flare. Indeed, they are super Eddington in the early phases. And they have luminosities declining with this power law. So in principle, they are very useful in order to detect, for example, quiescent black hole. So the tidal disruption event that triggered this study was detected by the SWIFT satellite, and it's SWIFT J1644. Its light curve was something, X-ray light curve was something like that. So we get the flux, the time in days. 1, 10, 100, 1,000. So the light curve was sort of, this is the typical, the time in time, and some authors argue that this quasi-periodicity with a period of about 2.7 days could be linked to the jet precession caused by the disk rigid precession around the black hole. So what we did was developing a model to describe the accretion disk that forms after the tidal disruption event and see if we can link the precession period to the black hole spin.
Sure, yes. Just to
Yes.
understand, right? So that emission over there comes from the jet, mainly.
Yes.
Mirage. So, and why does it scale like t to the minus factor? Is it because the viscous time scale is way shorter than
Yes. Yes, indeed.
than
Yes, indeed.
40 days or something
Yes,
like that?
indeed.
Okay.
So we can assume that
Because the disk was
the
that
debris are like processed very rapidly by the accretion disk. So hydrodynamical simulation show that the stellar debris orbit circularize at the circularization time radius, which is about 2 times the tidal radius. So basically this fixes the outer radius of the disk, which in units of the gravitational radii is just a function of the black hole mass. Then the disk extends towards the innermost stable circular orbit, which again in units of the gravitational radii is just a function of the black hole spin. So if one does the math between these two, the outer and the inner radius, we realize that the disk is expected to be narrow. So we can reasonably assume that it will be entirely radiation pressure dominated. This according to the Shakur and Sunyaev model of accretion disks. So we said that initially the accretion rate is above the Eddington threshold. So the disk is expected to be hot. So it's expected to be thick, geometrically thick rather than thin. So basically we thus assumed a slim disk model. So like we took a slim disk model taking into account also the advection of photon inside the disk. And we then modeled the super Eddington phase of the accretion flow, requiring that there will be an outflow because the accretion rate is above the Eddington threshold, but we modeled this phase requiring that the disk luminosity, the local disk luminosity is always limited by the Eddington value. So by requiring this, the accretion rate in units of the Eddington value increases with radius during the super Eddington phase and then declines with time as the fallback accretion rate does afterwards. So then this accretion disk has a surface density profile which is proportional to R to the minus P, where P is 3/5. And this comes requiring that the disk is radiation pressure dominated, and then the sound speed goes with R to the minus Q, where Q equal to 3/2. Okay. So.
Just a question.
Yes.
So, are you assuming that there's an inflow which is Eddington limited, and everything else is flying out?
Yes.
Is it rejected?
Yes.
Okay. So that means there are beams like as a function of radius.
Yes, exactly. Okay, so since in general the stellar orbit is inclined with respect to the supermassive black hole spin, this is the angular momentum of the black hole, then the angular momentum of the disk will be inclined as well. Since the two angular momentum is aligned with respect to each other, they couple, and this coupling is known as the Lense-Thirring effect. So and this causes the precession of each ring of the accretion disk with a frequency given by this relation. So since the precession frequency is inversely proportional to the radius of the third power, we can see that the disk inner parts are subjected to a more strong torque, so they will tend to align with respect to the supermassive black hole spin, while the outer parts keeps the original misalignment. So the result is a warped disk. Like that. I mean, this is large. Typically, the warp are very small in this kind of systems. Okay, so since the disk is thick, can I talk here? Since the disk is thick, the warp disturbances propagates inside the disk in the so-called bending wave regime. And this regime is defined basically by the fact that the aspect ratio is greater than the viscous parameter. So in this regime, the work propagates as a bending wave with half of the speed of sound. So the work propagation time scale is given by 2r divided by cs, which we can write as a function of the aspect ratio, gaining 2 over omega h over r, the minus 1. So since this number is relatively large, the work propagation time scale can be short enough to allow the work to propagate efficiently inside the disk. So each ring of the disk will process with exactly the same frequency. So the accretion disk will process as a rigid body around the black hole. Okay, so in order to see this rigid precession, we solved the equation that regulates the work propagation inside the disk in the bending wave regime with the monodimensional ring code. And what we did found is something if we wrote the x component of the disk angular momentum versus time, where there is 0, for 4 different radii inside the disk, we see this sort of behavior. So on. So we see that 4 different radii inside the disk process with exactly the same period. So this means that basically the disk is rigidly processing around the black hole. So if this occurs, we can evaluate the total, so the local torque exerted by the black hole onto the disk is given by this product. So then we can calculate the total torque, and so the total, the global precession frequency.
Just a question.
Yes.
What do you assume about the viscosity? Is it completely negligible?
We assumed the Shakura Sunyaya viscosity. We didn't.
Okay, so but what equation are you solving? When you, what is the, so you need to understand that what you plotted.
Okay, so I will write the equation. Okay, so. Where L is the angular momentum of the angular momentum versor of the disk, and G is the internal torque. So these are the linearized equations that are valid just for small works. So basically the code solves this kind of equation both in time and space domain. And then what you get is the angular momentum of the as a function of the time.
Another question, why the disk should be inclined?
Because the stellar orbit is inclined. I mean, typically, there is no reason for which the star has to have an orbit perfectly aligned with the data speed.
So here omega is the Keplerian velocity, or is it the?
Yes, it is. Yes, it is.
And where is the black hole? Which term is the Lense-Thirring precession term?
So this. one. In which again, this one is inverse convolution, so it's a little.
And G includes viscosity.
Yes. I mean, there is no viscosity there.
And which value did you choose?
Sorry?
Which value did you use for alpha?
For alpha, 0.05. Yeah, I mean, one has also to consider the fact that this relation has to be valid, so.
Bence is taking notes.
Okay.
We should allow the selfies.
The? Okay. Okay, so. So the global precession frequency is given by the total torque and so this one, this outer radius is a function of the black hole mass only. This is a function of the spin only. So what we did is to compute the precession period as a function of the black hole parameters. And the result is, if I draw the precession period in days as a function of the black hole spin for both prograde and retrograde orbits. So here we have 1 day, and up here we have 10 to the 3 days. For retrograde orbit, we get something that goes like this. While for prograde orbits, we have something that goes like this. This is for 10 to the 5, solar mass is black hole. 10 to the 6, and 10 to the 7. So if, for example, for 1644, we measure a period of about 2.7 days, which is roughly here. Okay. So if we assume that from the light curve in principle, one can infer the period of periodicity and the mass of the black hole. So if this is 10 to the 7 solar masses, then here we gain a spin, which is 0.7. If this is more close to 10 to the 6 solar masses, then the period, the spin is 0.9. So what we did was, yes.
Can you remind us how you compute the route?
From the circularization radius.
So that's the circularization
Yes.
radius, and then you suppose that
Yes.
these three.
Yes. Yes. I mean, it's of course the right thing to do was letting the outer radius evolve with the viscous time scale. That's what we are doing right now. So, but we don't have the results yet. And yeah, because I mean it's like a very simple approximation to assume that the disk boundaries are fixed. It's just for solving the equation in the simple case. Okay, so.
But so this outer radius does not depend on the initial condition of where the star came in?
No. I mean, well, Yes, because it depends on the tidal radius. No, no. Sorry, no.
So it's always twice the tidal radius with
Yes,
respect
we
to
assume that it's like that. But then, I mean, I think that hydrodynamical simulation take into account these things. So changing the impact parameter might change the circularization radius slightly. I mean, we assume that it's 2 times the tidal radius, but it's not like a...
So you're effectively assuming beta equals 1.
Sorry, yes,
Yeah.
yes,
Yeah.
sure, yes.
Okay.
Sorry, I should have said that. Okay. So basically, what we can do is to link an observable, which is the precession period, directly to the black hole spin, once, of course, we know the mass. However, simulations and analytic estimates show that the disk might not rigidly precess. So it might be tearing in different rings, each one precessing with its own frequency. So basically, from previous work, the condition that needs to be satisfied for the disk to rigidly precess is just that the precession timescale evaluated at the inner radius is greater than the warp propagation timescale. However, we thought about this like for months, and so we came up with the following solution. So in order to warp a disk, each ring has to tilt by at least order h, right? Because the disk has a thickness. Then to warp the whole disk, each ring has to precess by h/r fraction of the full period. So this condition actually is factor k, which is independent by the parameters of the system. h/r is 2 pi over omega p, all evaluated at the inner radius, to be greater than the warp propagation timescale, which is the sound crossing timescale. So it's this is the condition that needs to be satisfied in order for the disk to rigidly precess. In order to see these, we performed several numerical simulations using the same ring code. So let's call this T-warping. If we plot T-warping against the sound crossing time, this is the criterion. So for the dots here, for which the condition is satisfied, we saw precession, while for the cross here, we didn't see precession. So this is the criterion finally.
So that's T warping on the y-axis, and
Yes.
the x-axis is
T-warp propagation is
T
on.
warping.
Not differential precession.
What?
No precession at all.
No, it was different, of course, it was different. No rigid precession, as you say. So in doing this, we changed the h/r alpha, the outer radius, and the spin in order to gain this. So several simulations. Okay. So so in order to to complete the study, we study also the alignment process. So now I erased it, but maybe you could have seen that the precession, the oscillation drops after some time, which means that eventually the accretion disk angular momentum end up aligned with the black hole spin. So there is no more coupling, there is no more Lense-Thirring effect, and there is no more precession. So this can occur for, there are two processes that might lead to alignment. The first one that was pointed out by Stone and Loeb in 2013 is the fact that since the accretion rate declines with time, then the disk goes from being thick to being thin. So it enters the regime in which h over r is smaller than alpha, and in this regime the viscosity will dissipate the warps before it can rigidly precess. So here the alignment is proportional to alpha to the minus 3/5, and we found that this is what occurs for spin value below 0.3, so for very low spin value. The other process that might be responsible is the natural viscosity that acts to damp the oscillations. So in this case, the alignment time scale is inversely proportional to alpha. And we saw that this happens for spin values above 0.3. In general, the other thing that we observed is that we found is that the alignment time scale decreases with the black spin. This is somehow expected because if the higher the spin, the closer is the ISCO at to the black hole, so the stronger is the torque, and so the alignment will be faster. So this makes sense. Okay. So in a similar way, the Lense-Thirring effect can be used in low mass X-ray binaries to do the same thing, to infer the spin value, or at least to place limits on it through the study of QPOs. So low mass X-ray binaries are double systems composed by a compact object that can be either a black hole or a neutron star, and that accrete matter from a companion through an accretion disk. So here we have the black hole, here we have the disk, here we have the companion. This is called the accretion stream in this picture, and this is the accretion disk. So most of X-ray binaries are a transient system, meaning that they alternate long quiescence period with short outbursts. So the important thing is that they do this on human accessible timescales, so we can actually study them by timing measurements. The variability of these sources correspond to significant changes in their spectra, and these changes are traced by means of the hardness intensity diagram. So the source does something like this hysteresis cycle in this way. So here's the hardness, and here is the intensity. We can thus distinguish four different states: the low hard state, the high intermediate mass state, soft intermediate mass state, and high soft state. Plus, here, there is sometimes an anomalous state, during which the luminosity is above the Eddington threshold, and that's been observed in a few sources. So basically, these four different branches correspond to four different types of spectra of these sources. So the analysis of the fast time variation in this spectra, in the power density spectra of the sources, basically allow us to characterize this state. In particular, the analysis of QPOs that are a very narrow feature in the PDS of these sources. And are divided in two main groups. So low frequency QPOs with frequencies, let's say, below 50 Hz, and high frequency QPOs that are above 50 Hz.
Excuse me, what is PDS?
Sorry? Power density spectrum.
Okay.
Okay, so low frequency QPOs are divided in three types, A, B, and C. Type A QPOs are found in the high soft state, and their origin is still unknown. Type B are found in the soft intermediate state and are associated with jets that are supposed to be launched by the source from the transition between the hard and the soft state. And then finally, type C QPOs are found in all states. And then high frequency QPOs are divided in lower and upper.
Sorry, when jet is home, could you explain?
Sorry?
What state jet is home?
This when
Physically, what happening?
what? Sorry?
That's the question. What happens physically in the disk that causes the launch of the jet?
Well, okay, so so the typical picture here is in these states you have a thin accretion disk, and then you have a sort of a huge torus. So this is, I don't know how to call it, but it's called an accretion flow. And then when the source goes from this state to this state, in this state this accretion flow becomes extremely narrow. So the thin disk will reach basically, we have the thin disk, a very narrow corona, let's call it, and then there is the black hole. So, well, it's not like very clear the mechanism that launches the jet. But
Transition phase.
Yes,
Something
yes,
happening.
yes, exactly.
What people speculating? Or?
I think so. I'm not up to date on this, but I think that so Fender in a paper, which is of 2009, so not like very recent, but this is the one of the paper that links type B QPOs to the jets. Okay, so there are several models that attempt to describe QPOs in general. One of these is the relativistic precession model. Or RPM.
So, Alessia,
Yes.
you said
Yes.
the high frequency QPOs, lower and upper refers to the frequency or
Yes.
so they are high frequency.
But yeah, but they are like, there is one that is lower now than the other. Okay, so this model was mainly done by Stella and Vietri in 1988 and 1989, and was then revisited by Ingram in 2009 and 2011. And it was used basically by Ingram and Motta to use QPOs to place limits on the black hole spin. And now I will come to how can we do that. So what I did is to place limit on the spin value of the black hole for several sources, looking for type C QPOs in the soft state. So, according to the rigid precession model, we have three frequencies that are associated with the motion of a test particle around a compact object. So we have the orbital frequency, which would be a function of the black hole parameters and of the radius at which it is emitted. We have the periastron precession, which is another function, again, of this parameter. And then finally we have the Lense-Thirring frequency, which is another function of the parameters. So these three frequencies, these three equations are three equations in 6 variables. So if three QP QPOs are detected simultaneously, so if these three frequencies are detected simultaneously, and we can assume that they are emitted at the same radius, because we are talking about the test particle, then the system can be solved exactly. However, as you can imagine, this is not the case. So, the system can also be solved with two QPOs, that is more likely to happen, and an independent mass measurement. However, for some sources we don't have an independent mass measurement anyway. So, what we can do is to just consider this equation, and that's what I did, associating, well, I forgot to say something, so this is associated with the upper high frequency QPO, according to the RPM. This is to the lower high frequency QPO, and it's associated to the type C QPO. So what I did is to look after type C QPO and to find the highest one, because then we can assume that in the soft state, since the thin disk extends towards the ISCO, so this frequency is associated to that of the test particle at ISCO. So we fixed the radius, we then assume a range of masses, and then we place limit for the spin, solving this equation.
So, you're assuming that the disk precesses like a solid ball, right?
Yes.
And the precession frequency is a sort of an average of all the precession frequencies from the inner radius to the outer radius.
Well, no. What we did was assuming that since the accretion flow is very, very narrow, we can associate the precession of this very narrow accretion flow to that of the test particle at ISCO. So that's why we were looking for the highest type QPOs.
So in this specific case, the circularization radius of the gas flow that comes from the companion circularizes at ISCO.
Yes, we are assuming that. Yes. So if we find the highest type QPOs, then this is emitted close to the black hole. So we can assume that it is emitted at ISCO.
Am I right saying that you're assuming that at the very least it cannot be closer than the ISCO?
Exactly.
Okay, and then you will draw some, I don't know, lower limit to the
Yes,
spin.
exactly. I mean, even if this is not true, so if the QPOs is actually produced at the closer radius, we are underestimating the spin. So our lower limit is still valid. Did I answer to your question?
So if you observe just the spectrum of the disk, is it possible to put some barriers on this?
Yeah, I mean, in principle, what one can do is to infer the transition radius between the inner hot flow and the thin disk from the spectrum. However, this is very, very extremely difficult. If one can, in principle, do that, then you have the outer radius and you have the inner radius, so you can use like the precession frequency and everything works out perfectly. But, however, unfortunately, this is not the case. So basically, what we gain solving this equation and assuming a very conservative mass range for stellar mass black hole, which is from 3 and 20 solar masses. So solving this equation for the mass and the spin couples, we find something that is like this. This is below 0.5. So this for different frequencies. For example, if this is 15 Hertz, and this is the highest type CQPO that we found for a given source, then putting an upper mass limit allow us to put an upper limit to the spin, and then again we have the lower limit, putting a lower limit on the mass of the black hole. So we constrain the spin within this range. So we did this for 12 sources.
But sorry, just to follow the logic here,
Yes.
you were saying earlier that you're using R ISCO as an inner bound,
Yes.
of course. But if the R is greater than R ISCO, then you could allow a larger A, right?
Yes. Yes.
Okay.
But then, I mean, so the point is, I look for the highest type CQPOs,
Yeah.
and then I put the lower limit. If this is not true, so there is another frequency which is even higher,
Mhm.
but I didn't found it for timing reason, for low resolution data or whatever, then my lower limit is underestimating the lower limit. I mean, I don't know what. So
Just completely larger, right?
Huh?
exactly.
Okay, but I mean, in terms of plate, so the lower limit, fine, but in terms of the upper limit,
Mhm.
if you're outside of the ISCO, A could be higher than your upper limit, right?
Yes.
So, and that's kind of tough to say.
Yeah. I mean, we are underestimating also the upper limit, so it can be larger. If this is your point.
Yeah.
Okay. Yeah, so by doing this, we found no evidence of highly spinning black hole because our upper limit was 0.555 for all the sources. So
And the lower limits?
the lower limits goes from 0.1. Well, the lower of the lower limits is 0.1.
So I would rephrase
Yeah.
whole sentence saying, is it right to say that you basically estimated that all the spin had to be larger than 0.1?
Yes.
Full stop.
Yes. Exactly.
Okay.
But it's not true that all the spins has to be this upper bound.
No, okay.
But I mean, it changes slightly with the frequency. So even if the ISCO is a bit higher, I mean, if this is not the highest type CQPOs, then we have another upper limit, but it's not that far away from from 0.55.
Is there any particular reason why the type CQPO should be associated with the Lense-Thirring precession?
Well, according to this model, this is what they do. No, there's no particular reason.
But are there some objects for which you measure,
In other ways,
no, the three frequencies and you check whether they are